with the sum of this Velmango function. Which is defined if n is a prime power to be log of the prime and 0 otherwise. And it's more or less equivalent to try to understand the sum over n less than x, n conquered to a mod q of lambda n. So the most important result about this to keep in your head is a conditional result. Conditional on the generalized Riemann hypothesis. There's a very straightforward proof using the explicit formula that this sum is equal to x divided by the Euler phi function of q plus an error term of size x to 1/2 plus epsilon. And the quality of this estimate depends a lot on q and x. If q is small relative to x, this is a very good estimate. It tells you pretty much exactly how many primes there are. And if q is greater than about x to 1/2, then this is a trivial estimate. It's kind of bad for two reasons. One is that the error term is bigger than the main term, and so it doesn't even tell you that there exists a single prime in this progression. But even more so, the error term is worse than the trivial bound, just using the fact that there's only x over q, n conquered to a mod q, and the Velmango function for each of them is at most the log of n. So this is the only really useful estimate for q less than about square root of x. And also, it's conditional. So unconditionally, we know a weaker statement. We know by Siegel-Wolfus a reasonable estimate for q less than like a small power of log of x. So much less than root x. And then we also, if you allow averaging over q, we can do much better. If you average over all q of size less than root x, then we have Bombieri-Vinogradov would give you an asymptotic for this sum on average. And in fact, depending on exactly what you mean by on average, we can do better than Riemann. We can let q grow, x to 1/2 plus delta for some delta reasonably small. There's a few different notions of average depending on like where you put the absolute values and weight functions and these kinds of stuff. And you get slightly different deltas for different definitions. So I want to talk about an analog of this involving polynomials over a finite field. So let me begin with notation. We're going to take q a prime power, fq the finite field of order q, and you can think if you want of a special case where q is a prime, so fq is just the integers modulo q. We're going to think that the analog of the integers in this setting is the ring of polynomials in one variable over fq. And the analog of the natural numbers or positive integers will be monic polynomials, polynomials with leading coefficient 1, which I'll denote with a little plus here. And when I want to work with integers of given size, the analog of that is monic polynomials of degree n, which I'll write with an mn. And we can think of this as specifically being the analog of an interval of length q to the n, because there are q to the n monic polynomials of degree n over fq. And the modulus, we can't call it the modulus q because we're already using q, so it's going to be a square-free polynomial of degree m, and we're going to call it g. And so to state an analogous result, the last thing I need is the Velmango function of a polynomial f is going to be the degree of pi if it's a power of a prime polynomial pi. So that would be a monic irreducible polynomial pi, and it will be 0 otherwise. Is going to be a technical restriction of the method of the results that I'm going to talk about shortly. It's not, for asking the question, it's not the most natural restriction. It's just a restriction of the method, and I'll tell you later where it shows up. Although not in an incredibly enlightening manner. I don't have a philosophical explanation for why that's an obstruction. So the first thing I'm going to do is I'm going to state the analog of this conditional bound on the Riemann hypothesis in this new setting. And the main thing that's changed is that the Riemann hypothesis is a theorem. in this setting. It was proven for Dirichlet functions by Vey. And so using this, you can prove the same estimate with a very precise error term. The sum over monic f of degree n congruent to a mod g of the Velmango function of f is equal to q to the n divided by phi of g plus an error term of size square root of q to the n times n. And you can be very precise. The error term is exactly at most m minus 1 q to the n over 2. And so again, for m small, m less than about half n, this gives a really good estimate. And for m greater than half n, this gives a really bad estimate that is worse than trivial. So, yeah, m is the degree of g, yes. M is fixed to be the degree of g throughout this talk. Again, n will be the degree of f. So you can think of the degree as like the log of the size. So square root size is the same thing as half the degree. So this is directly analogous in terms of the ranges in which it's applicable to the Riemann hypothesis estimate that I gave you in the integer setting. But on the next slide, I'm going to do better, at least for some values of q. So this is a theorem, and it's a kind of complicated statement. And so I want you to look at the last line first. So the last line says, really what we want to be proving, we have Velmango function summed over f congruent to a mod g is equal to the expected main term q to the n over phi of g plus an error term, which is going to be a power saving size. So the main term is of size q to the n minus q to the n, or divided by q to the n. And so we want our error term to be smaller than q to the n minus m by factoring the exponent of 1 minus delta. So that's the estimate that we would like to prove and that we can prove. And then the first few lines are going to be explaining when can we prove this? What conditions do we need to get such a nice estimate? So the picture is we're going to have g of degree m, and m is going to be at most theta n. So the key parameter here is the ratio theta between the degree of g and the degree of our polynomials f. And we can get this estimate if q and theta satisfy the following inequality. Q greater than 4 to the 1 over 1 minus theta, 1 over 1 minus theta minus a half squared times e squared. And in that case, I know there exists delta greater than 0, which gives me this power saving by delta estimate for any square free polynomial g of degree m and for any residue class a mod g. And the power savings are even explicit.
How explicit is delta?
It's given by this formula right here. So it could not be more explicit. I just wrote the formula. It's given by 1/2 minus log q of this particular function of theta. And so
in some of the other words, q had to be a power.
Yeah, that actually is mentioned on the slide. Yes. So previously with Mark Chesterman, q, we had a function of q and p. So q is a power of p, and we had q greater than p squared times something. So this inequality was never satisfied unless q was a power at least 3 of p. And even if p is quite small, this inequality is a lot worse than this inequality. I mean, it's not obvious because this is an exponential and this is only rational, but this is going to infinity much faster. So
what question was asked?
Nice.
Sorry, what should I repeat?
The question that was asked, whatever question was.
Oh, so the question was, in previous work, didn't q have to be a power of p? And so I was explaining that is true, and it's explained on the last line of the slide, but that's one of the improvements we made over the previous work. And the other comment I want to give is that q does not have to be that large for us to get a non-trivial estimate here. We can beat theta equals 1/2 for q greater than 266. So there's really very few finite fields where this doesn't work. And I guess the only other thing I want to say about this is that this estimate was proven also for square-free polynomials, but we could have proven it for non-square frees. We were just too lazy to. Whereas this estimate, there's a real technical restriction. So one advantage that this older estimate does have is we could have proven it for non-square frees probably. And so we can actually do very similar things, not just for Velmangos, but for other arithmetic functions too. So I'll give two examples of two more estimates we can prove by the same method. So the first one has to do with the Mobius function, which the Mobius function is of a polynomial f. If you factor it into r distinct prime factors, it's going to be -1 to r, and 0 if you can't factor it into r distinct factors. And we'll get the same kind of estimate. We'll get a sum over mu of f, a sum of mu of f over f congruent to a mod g of degree n, of O of q to the n minus m to the 1 minus delta, as long as m is the most theta n, under conditions on q and theta. And the condition is simply that q is greater than e squared times 1 plus theta squared divided by 1 minus theta squared. So as theta goes to 1, our requirement for q is going to infinity, but not very rapidly, only kind of quadratically rapidly. And so again, you can have a explicit power savings if you want, and you can see that the Q inequality I've chosen is exactly the inequality that's needed for delta to be greater than 0. So there's kind of nothing hidden there. Here you can beat this Riemann bound of 1/2 already for Q greater than 66. So already on for 2-digit primes, we can do better than Riemann. And again, we had a previous result with Schusterman on this problem.
Riemann is the half, right? Why is this one complicated? Riemann is half, right?
Yeah.
N minus M, 1 minus
So yeah, Riemann is like the theta equals 1/2 case. M equals theta over theta. So if you plug in 1/2 here, you get e squared times 9, I think, which is about 66.
You mean Riemann is how large the modulus has to be at, right?
Yes.
For the error terms, are you essentially producing the best estimate of the sum range?
So no. So we do, so if you fix theta and you let Q grow large enough, this power savings goes to full square root cancellation. And with Riemann, you don't get full square root cancellation unless the modulus is very.
That's square cancellation for some range beyond what seems to be.
I'm not super confident in this, but I would believe that square root cancellation should be true for any, at least for any theta. For any power, for any theta strictly less than 1. And yeah, so we had a previous result with Schusterman on this one also, where you had just throw a factor of p squared in there, and that one we did actually write up the non-square free moduli case. And the last result of this form that I'll write down has to do with the divisor function. The divisor function is the cardinality of the set of k tuples of monic polynomials whose product is your f. So it depends on this parameter k. And here you see a little bit more complicated version of the formula for the main term, and this is the formula that works in generality. The sum over the f congruent to a mod g is equal to the sum over f relatively prime to g of the divisor function divided by the number of residue classes relatively prime to g plus a power savings error term again. And here the range of cancellation is now this function of k and theta. So q greater than e times k minus 1 squared times theta squared over 1 minus theta squared times k to the 2 theta over 1 minus theta. Yeah, all the decompositions into a product of k factors. So for k is 2, we're just counting divisors. And for k greater than 2, we're counting decompositions into a product. What do you say?
With ordering?
With ordering, yes. I don't think it really matters. I think without ordering, you get a very, very similar result, because for most decompositions are going to be, all the permutations of them are going to be without repetition. All the permutations are going to be different. There's going to be very few decompositions with repetition. So it'll just be off yeah, it'll just be off by a factor of k factorial. So I want.
DK is that, okay?
Yeah.
DK is a,
Ketuples.
no, it's a Fourier coefficient of a modular form.
So yes, you're asking, could I do for a modular form other than an Eisenstein series? The answer is that I hope to do that in future work, but I have not worked out all the details. And with some conditions on the modular form, which are not too exciting. But what I want to talk about here, I want to try to, especially for the people in the room who are not analytic number theorists, I wanted to explain how this connects to Gala theory. So how are we able to prove results simultaneously for a bunch of different arithmetic functions at once? Oh, can we take it off? I can certainly make it much smaller. And put it in the corner. There's a single theorem which implies these three different statements, and the way to do that, you need to set up a framework that incorporates all these functions, and this is done using the symmetric group. So let me remind you that a polynomial of degree n over fq join t, typically, not always, but most of the time, has n distinct roots over the algebraic closure of the finite field fq. And there's an element of the Gala group, the Frobenius element, is going to always permute these roots. That gives the conjugacy class in the symmetric group Sn. And the way that this conjugacy class will look is it'll have one cycle of degree d for each irreducible factor of f of degree d. And then that enables us to define nice functions on polynomials given functions on conjugacy classes in the symmetric group. And the best functions on conjugacy classes in the symmetric groups are characters of representations. So for representation rho of the symmetric group, we have this function f rho of f, which is defined to be the trace of this Frobenius conjugacy class of f acting on rho. And then we need to do something to extend this function from the roots, the f where with all n distinct roots, the square tree f, to the f where the roots have some multiplicity. And then you have to do something which is a little bit weird, but turned out to give you really nice formulas. And what that is to kind of label the roots and label them with multiplicity so that the roots that have high multiplicity get more than one label. And you look at all the permutations on the labels that are kind of consistent with the Frobenius action. So they send at least one, they send all of the labels of a root x to all of the labels of, to all the labels of Frobenius of x. So you get not just one permutation, but many permutations. And you simply define f rho of f as the average of the traces of all these permutations acting on rho. And that lets you extend it to a function on all polynomials. So these f rho functions lets us write the three arithmetic functions I was considering in terms of very nice representations of symmetric group. So the Velmango function, it turns out, is the alternating sum of the trace of the wedge powers of the standard representation on the Frobenius conjugacy class, which is another way of saying it's a characteristic polynomial of the Frobenius conjugacy class acting on the standard representation evaluated at 1. So this function vanishes if and only if 1 is an eigenvalue of this permutation matrix. Of Sn, the n minus 1 dimensional. So the permutations which have a eigenvalue 1 on the n minus 1 dimensional standard representation of Sn are exactly the n cycles. Which don't have the eigenvalue 1 are the n cycles. And so those are the ones where this coefficient is non-zero.
Question: is there any chance? I know Velmango classically uses the lambda. Is there any chance the lambda is related to that wedge product?
I don't think so, no.
Okay.
Good.
I don't know what Velmango used that.
Well, there are a couple of examples of this kind of prescience, right? There's like different areas of mathematics where people use the letter Q for things, which were then later connected. And like, I guess sometimes something just really feels like it should be the letter Q. The Mobius function is the simplest one to express. This is the f of the sign representation times -1 to the n. And so this is expressing some classical identity that -1 to the n times the sign of a permutation of Sn is -1 to the number of cycles. Sign is also the last coefficient of the characteristic of the characteristic polynomial. Is that what you're saying? Oh, they should say, yeah, they should say mu of f is a sign of sigma f, I guess, not lambda f. And then the divisor function, you have to do this, take the n-fold tensor power of a k-dimensional vector space and let Sn act by permuting the n tensor factors. And then the trace of a permutation in Sn is going to be the number of like k colorings of the numbers 1 through n that are fixed, which is k to the number of cycles. And that's k to the number of prime factors of f, which is the same thing as the divisor function.
Jumping ahead to what you're going to do, and that's the coefficient of a modular form, what would be your expression here? You wouldn't just use the symmetric group. So you would do the symmetric group. I would end up with symmetric group representations times something else, and the something else would carry the modular form. The other thing would be some representation of the dual group.
Yeah, I guess. I mean, so it would be representations of the Gala group of SQ adjoint T, which, yeah, I mean, I don't want to actually work. I don't want to do work on the automorphic side for this. There would be Gala representations, and then if you ask me to do something with an automorphic form, I would call upon Laforgue's theorem. But if that answers the question. So the statement of the main theorem, it unfortunately uses some functions which are complicated and annoying to write down, and I don't want to torment you with. But these are complicated functions which depend on a representation rho of Sn, and they're defined using primarily Schur-Weil duality. And then we get an estimate for the sum of an arbitrary arithmetic function f rho over f congruent to A mod g, minus the expected main term, which is the sum over all in f relatively prime to g times 1 over phi of g. And we get an estimate where the error term is exactly square root cancellation q to the n minus m over 2 times these factors depending on rho. C1 of rho plus C2 of rho times root q. Then we have to throw in a factor of 2 in there. So this is a theorem. It will be a theorem once I write, if I were to write down the definition of C1 and C2, which I don't want to do. And then you can specialize it to the 3 statements that I gave previously by calculating C1 and C2 in those particular examples. And so, sure. Well, I can tell you C2. C2 is not so bad. It's C1 that's really bad. So what you do for C2 is you take an n-1 dimensional representation, or sorry, an n-1 dimensional representation, and you tensor that up to n to get a representation of Sn. And you tensor that with rho, and you tensor that with sine, and you take Sn invariant. And so this is a representation of GL m-1 is acting on this. And you take the trace of the following matrix, lambda 1, lambda 2, up to lambda m-1 on the diagonal, 0 is above the diagonal, 0 is below, acting on this representation. And then you take the derivative with respect to the variables lambda 1 through lambda m-1, and then you evaluate the variables equal to 1. So you tensor with sign representation, then you take the Schur-Weil dual representation of GL m-1 minus 1, you take the character, you apply a derivative, you evaluate the identity. That's C2, and then C1 is more complicated than that. But that's an idea of what C1 is. So
what I have to do and specialize this is to give like a nice formula for this character and then calculate its derivative. So you get these generating function manipulations. I'll say something. It's a pretty long paper, so I won't give all the details, but I will tell you some ideas about the proof. Yes, I will tell you why it is only a root q here and not a root q squared, at least with some level of detail. In fact, that's what I'm going to do right next. So the strategy here is first, well, both sides are going to be additive in row. Like this is certainly an additive function in row, so it suffices to handle the case where row is irreducible. And for row, we're going to split into two cases. Because for some irreducible representations row, like the trivial representation, this sum is independent of x. So the trivial representation, you just get the constant function 1. This sum just tells you the number of parameters of the progression. It's independent of x. So for these ones, we have a main term and no error term. And so for the remaining row, we have an error term and basically no main term. And so what we do is we throw away the row that don't cancel, and we have to try to show the remaining row do cancel. And the next thing we do is we apply the Lefschetz fixed-point formula. And that lets us express this sum as the cohomology of a certain variety with coefficients in a particular sheaf. And this argument, if you're sort of initiated, if you understand how the Lefschetz fixed-point formula works, this can be done in a relatively formal way without requiring a great amount of creativity. The creativity is all in how you actually understand the cohomology groups. And then we always use in these problems the Leans-Rhema hypothesis, which says the eigenvalues in cohomology in degree I are bounded by q to the I over 2. So if you know a bound for the eigenvalues of an operator to bound the trace, you need to bound the dimension of the space it's acting on. So the main thing is that we have to understand what are the cohomology groups of the relevant variety with the relevant sheaf for understanding this problem. And so the key claims that I can prove out the cohomology groups are the first one is that it's concentrated in degrees n minus m and n plus 1 minus m. The second one is in degree n minus m. Its dimension is bounded by C1 of rho. The third one is in dimension n plus 1 minus m. It's bounded by C2 of rho. So this first fact that the cohomology is concentrated in the 2 degrees n minus m and n plus 1 minus m is the reason that it only had a single power of root q there. Although, of course, I haven't yet explained to you why I can prove the cohomology is concentrated in degrees n minus m and n plus 1 minus m. And I'll say a little bit about that on the next slide. So I rewrote my three geometric claims: cohomology vanishing, bound in degree n minus m, bound in degree n plus 1 minus m. And it's very important for proving these claims, as far as I know, that you don't try to prove them directly. What you want to do is understand how the cohomology group changes as A varies. So you're interested in the set of residue classes A, which geometrically forms a torus, and you're interested in how things change as you move from one point to another on this torus. You'll have a family of varieties parameterizing a varying family of progressions, and it's much easier to understand the change from one to the next than to understand any one of them individually. So to get anywhere with this variety, you have to compactify it. I found a compactification where the singularities I added at infinity to compactify are very nice. So they look like a toric variety. And the original variety has singularities that are nice in a different way. They're isolated. And that isolatedness of the singularities is the key thing that means we only have cohomology in a very small number of degrees. And to convert this kind of elementary geometric information of this about like isolated singularities of varieties into information about cohomology, I need to use a bunch of cohomological tools. So we have, for parts 1 and 2, I really only need tools from back in the 1970s, which, you know, depending on, you may or not think of that as ancient history, such as branching cycles of reverse sheaves. And where for part 3, I really need techniques from the past few years, that being Saito's theory of the characteristic cycle and characteristic T. And so the reason that square freeness is used, it's actually only used in the construction of the compactification. So I could do something very similar for other kinds of progressions if I could find a good compactification of a certain variety, but I don't know how to do that.
Well, you say how A varies. Do you mean like understand the worst one, like compare and change the best one, or do you understand them all by averaging in some way?
Okay, good question. So what I mean is I want to use vanishing cycles to compare the worst one to the average one, and then to understand the average one, there is a step where I need to, sorry, to the generic one, where I go to the average and I take the cohomology of the whole torus with coefficients, and I use that to get some information about the generic one. But I mean, it's using the characteristic cycle in the way that you expect. That was a singular U and not a plural U. Yes. So I gave a previous talk after which someone asked me, how does this compare to the previous results that like I proved, which I wouldn't normally do, but I thought people would want to know, in part because I've given a number of talks here about some previous results. I want to say, how does my new result differ from what I did before? So in this work with Shusterman, we proved a lot of things about the Mobius function. And the main thing we were doing there, we had a surprising identity, which related Mobius to quadratic characters. And so we didn't attack the problem by just immediately plugging it into geometry. We first used this magical identity, and then we plugged our character sums into a geometric machine. So that work only enabled us to handle the Mobius function and also to handle some results about Velmango function by reduction to Mobius function. So in that sense, it was much less general. But on the other hand, my work with Shusterman could handle sums that are much more general than sums over arithmetic progressions. So we could handle a much less general class of functions, but over a much more general class of progressions, we could handle sums over polynomial progressions.
You don't have Gala with primes.
Correct. I do not know how to prove. We prove twin primes. I don't know how to prove prime triples, and I don't know how to prove higher correlations of primes. I still don't know how to prove prime triples, and I don't even have any ideas that I'm working on to prove prime triples. But maybe someday I or somebody else will prove prime triples over function fields. And then I also had some work just by myself about sums in short intervals of arithmetic functions, and that work was actually more similar in terms of geometric strategy. I was inspired by that, building on that. The main difference is use a completely different compactification. So I would like to sort of combine these two compactifications to handle the general case. I have no idea how to do that. And because of the nature of that problem and the nature of the compactification, we got less cohomology vanishing in the prior work and a worse Betti number bound. In particular, I only got real estimates in the large degree limit for the divisor function, not the Mobius and Velmango functions. So again, in that work, I could do a more restricted class of arithmetic functions than I can do in this work. But did I not have a slide at the end here? Okay. So I meant to have a slide mentioning the comparison to past works over the integers, because a lot of the results I've proven have analogs, usually somewhat weaker, over the integers, and a lot of different people have proven them, and I wrote down a list of a bunch of those, but I guess it's not in my slides. So, I mean, I'm sure that Here, you can tell people some of them, but I respect all the work. I respect all the work of people who did results over the integers, in addition to this finite field stuff. And then the last thing I want to talk about is a different kind of application, which demonstrates like the power of what you can do when you have access to very general arithmetic functions. And it's an application that I can describe, luckily, without this kind of like mysterious representation theoretic formula, although you'll see there's some other slightly mysterious formulas in it. And this has to do with this notion of factorization types of polynomials. And so the point of view is that if we're looking at primes, we're looking at polynomials which have a specific kind of factorization. They have a factorization to a single prime factor. But you could look at all the other kinds of special factorizations. You could look at polynomials of degree 20 that have a product that are the product of a prime of degree 13 with a prime of degree 7, or any other tuple of numbers you choose. You could look at polynomials which factor into exactly that tuple. We like to prove something that applies to all of these at once. So then we define, I'm going to borrow a definition from Ophir Gordetsky of the notion of the extended factorization type of a polynomial. And so what this is defined to be, if your polynomial is a product from I equals 1 to r of distinct primes pi I raised to exponents ei, I'm just going to remember the multi-set of ordered pairs, degree pi I comma ei. So remember the degrees of the prime factors and their multiplicities. And this lies in some finite set, EFTN, which is going to be the set of all multi-sets of ordered pairs where the product sums to n, because that's what you need for the degree to sum up to n also. So I want to look at the distribution of the extended factorization type of a random polynomial. I want to think about this probabilistically as a random variable. And if I take my random polynomial to be a random polynomial f of degree n, or maybe a random polynomial f of degree n prime to g, this is not that hard a problem. There are formulas for the distribution. And the strategy is pretty simple. Use the prime number theorem. You count primes. You then count the number of different ways you can multiply. The number of polynomials is the product of a prime of degree 5 and a prime of degree 7 is the product of the number of the primes of degree 5 times the number of the primes of degree 7. And that gives you a formula. So that question is not so hard. A harder question, if we look at polynomials only congruent to A mod G, a random polynomial congruent to A mod G, what is the distribution of the extended factorization type of F? That's harder because you can't answer just by multiplying the other primes because you don't control the residue class very well when you're multiplying them together. So you have to do something else. And so what we're going to do is basically give an answer to the second question by bounding the difference between question 1 and question 2. And so that the smaller the difference, the more we'll understand question 2. So the theorem, it's a little complicated to state. So we're going to be, again, we have g of degree m squared free. M is going to be less than or equal to theta n. A is still a residue class mod g. And we'll write down two probability measures. One is the average over all f congruent to A mod g of the point mass at the factorization type of f. So this is the measure of the distribution of the factorization type of a random f congruent to A mod g. And here, we'll write down the measure of the distribution of the factorization type of a random f relatively prime to g. We'll get that by summing over f relatively prime to g, the delta measure of the factorization type, and we'll divide by 5gq to the n minus n. And we're going to compare these distributions in the total variation distance. And what I might like to prove is that the total variation distance goes to 0 as n goes to infinity. Unfortunately, I don't know how to prove that. So what I proved instead is the total variation distance is at most a term that goes to 0 plus a term that depends on q and theta. And will go to 0 as q goes to infinity. So this formula is a constant times this function of L. We have an L to the L in the bottom, in the denominator, which dominates exponential, and L dominates a polynomial L, where L is itself a complicated function of q and theta. It's 2 minus 2 theta root q over 1 plus 2 theta times e to the 1 minus theta. So it's roughly, if you just fix theta and look at q, it's going to be growing like a small power of q, the 1 minus theta over 2 power of q. So
once q, if theta is like 1/2, then once q gets to around like 1,000,000, this starts getting pretty small, around like 0.1. And once q gets to like 1 billion, you know, 1 trillion, then it starts getting really, really small, and the error term is like pretty good. You get like 99%, you know, or 99.9%, or like something like that. You get pretty good similarity between these two distributions. But you can never get 100%, except if theta is less than 1/2. Then an estimate was given by Gorodetsky. Here it's decreasing very rapidly to 0. So Gorodetsky estimate is done using the Riemann hypothesis. And so I'm doing a beyond the Riemann hypothesis version of that. And because going beyond the Riemann hypothesis while simultaneously handling kind of an arbitrary factorization type is pretty difficult, I get this weird error term. So the starting point of our strategy for this problem is to handle one extended factorization type at a time. For each type, we want to bound the amount that the frequency of that type can decrease when we start the frequency at all polynomials and restrict to a progression. And so that uses the fact that you can determine the total variation distance by only counting decreases and not increases, because the increases are bounded by the decreases. And so there's a pretty natural approach to count the extended factorization type, which is to use a convolution of copies of the Velmango function. So the Velmango function more or less counts primes. If you convolve them, it will more or less count numbers, polynomials of the given factorization. So rather, I mean restricted Velmango functions, or restricted to polynomials of degree n. So if you want to count primes of degree 5 times primes of degree 7, you restrict Velmango to primes of degree 5 to polynomials of degree 5. You restrict it to polynomials of degree 7. You convolve the two, and that gives you a good estimate, an approximate estimate. And then you've got to sieve out the prime powers. So we don't, if we want a prime of degree 5, we don't want a fifth of power of a prime of degree 1. So we've got to sieve that out. Although sometimes we do want a prime power, depending on our factorization type. If our factorization type tells us we should have a prime power, we got to do something else. So there's one step of the argument, which is a kind of classical analytic argument. It's just a sieve to handle prime powers. And the reason we're doing that sieve is because convolutions of restrictions of the Velmango function are exactly the kind of functions that I know how to bound using the main theorem. They correspond to certain representations, and we can control the C1 and C2. But the bound we get for C1 and C2, it depends on the factorization type. So for some factorization types, our bound for C1 and C2 is very small, and we get a nice power savings estimate. But for others, it's very large, and we get a trivial estimate. So, and the determining factor is this cool invariant of the factorization type, which I call the entropy, because it's very closely related to entropy of probability distribution. So it's the sum for pairs AB, the sum over sometimes B, A over N times log A over N. And if this entropy is greater than the cutoff log L, I don't get a power savings estimate. And so for these types, what we have to do is use a trivial bound. We say the factorization, the frequency can't decrease as you go from all polynomials to a progression. It can't decrease by more than its starting frequency, because the frequency can't be negative. And so the second part of the error term, the harder or the larger part of the error term, is then counting the total number of polynomials whose factorizations have entropy greater than this cutoff. So we want to count their frequency overall, so we know how much decrease there can be.
What is M again?
M is the degree of G.
Oh, no.
Oh, sorry, capital M. Sorry, okay. Oh, sorry, capital M is a multi-set. So this is a factorization type is a multi-set. So I will write the definition again in a different context, and I think it'll be more clear there. So let me go to the next one. So the problem that we need to face, let me say, is to bound the number of polynomials of degree n whose entropy is greater than log L. We can define the entropy of a polynomial, writing the product of prime factors as the sum over prime factors, log of the degree over the degree f times degree over degree f with a minus sign in front. And so if you express that in terms of the factorization type, you get the formula I wrote on the last slide.
And so this is a purely elementary problem. I'm not going to use any geometry to attack it. And so it's a problem we can look at the analog over the integers that I think is at least a little bit interesting. So we're trying to understand a bound for the number of numbers of large entropy, where the entropy of a number is the log of its prime factor over log n times log of prime factor over log n summed over prime factors. And so, there's a very nice tool that we can use to understand the distribution of the entropy, which is called the Poisson-Dirichlet process, which is the known formula for the limiting distribution of the size of the prime factors of polynomials or numbers, or even permutations, a bunch of different stuff. And the way this works, you choose your first y1 uniformly in between 0 and 1. You choose your next variable y2 uniformly between 0 and 1 minus y1, y3 uniformly between 0 and 1 minus y1 minus y2, and so on. And then the sequence y1, y2, y3, etc., is the limiting distribution for the sequence degree pi 1 over degree f, degree pi 2 over degree f, etc. And I can mean that in two different senses. I can mean it as an unordered sequence of real numbers, or I could also mean it as an ordered sequence, but I would have to give this a funny probabilistic ordering, not the kind of the most obvious ordering you can think of. And so using this convergence and another little analytic estimate, we can show it to bound the probability that a number or polynomial has large entropy. It suffices to bound the probability that a random sequence, according to the Poisson-Dirichlet process, has large entropy. And this is going to be the yi log yi. This is just going to be some y log y with the minus sign. So this is now, it's no longer even number theory, it's now a purely probabilistic problem. And I looked in the probability literature, and I didn't find a solution to this problem in there. That certainly does not mean it doesn't exist. I don't know. But so I had to solve it myself. And so the method that I came up to solve it, I think is very fun. It's to use this Markov chain. So what we can do is we can take our sequence, y1, y2, created by the Poisson-Dirichlet process, and we can create a new sequence by kind of shifting one to the right, multiplying, adding this new variable x, and then multiplying the remaining ones by 1 minus x, where x is uniformly random, independent of the y's. And this step preserves the Poisson-Dirichlet distribution. If our variable is distributed by the distribution before, it'll still be distributed after. And so the thing to understand is, how does the entropy behave under this step? And the entropy actually itself forms a Markov chain. The only thing you need to predict the entropy after is the entropy before. And it behaves really nicely. So the exponential of the entropy can only increase by at most 1 each step of the Markov chain. So it increases very slowly. And this is intuitive. You think of the x of the entropy as like the number of possibilities. We're only adding one new possibility. So it can increase by at most 1. And then it can increase by most 1, but it usually doesn't. And the higher the entropy, the higher the probability it decreases in a given step. So if you combine these two facts, you can be pretty convinced that it probably will not, it's probably not going to have a high probability of being large, because to be large it has to increase by 1 for many steps with an increasing probability of going down instead of increasing. So, but you need to prove that. And the way I can prove that is by writing down another Markov chain, which is much simpler. The entropy of this new Markov chain only takes integer values, and it only goes up by 1, stays the same, or goes down by 1. And I choose the probability so that it always increases at least as fast, but it still doesn't increase very fast. It still has a very small probability to increase it. And because we're only going up by 1, staying the same, or going down by 1, I can just explicitly solve for the stationary distribution. We prove tail bounds for that by just summing, and then we can deduce bounds for the original distribution, and that gives this very weird formula for the error term that I wrote down in the anatomy theorem. Thank you for inviting me to speak.
Concerning this last part, have you looked at the work of Kevin Ford?
I don't think so, maybe.
He studied these great depths in the anatomy world integers gives this replay for some process. I suspect you might have seen something. The whole tree's got a very, very sophisticated probabilistic picture there. That I would imagine should at least improve it.
Okay, yeah, I'll look into that.
You talked about some variety and some sheep and some simplification.
Yes. Do you want me to tell you?
What are they?
Okay, so I was a little bit lying because there's really two varieties that I care about. So the variety is just the space, the moduli space of polynomials, such that f is the first variety. F is congruent to A mod G. So this is just an affine f degree f equals n, and it's monic. And so the way you should think of this is, oh yeah. So the way you can, oh, the other, there's a, yeah, turn the lights back on. Yes, that's probably much better. So the way you can think of this is like the coordinates for the space this variety lives in are the coefficients of this polynomial. And this equation, f congruent to A mod G, is like a linear equation in those coordinates. But then this variety has a cover where you go to complete factorizations. So or orderings of the roots, because that's the SN cover I'm interested in. So we have this variety. The coordinates are now going to be the roots. So we have alpha 1 through alpha n, subject to the condition prod I equals 1 to n, x minus alpha I is congruent to A modulo G. And this is now a polynomial equation in the alpha i's. Because you expand everything out and you do polynomial long division to do this congruence. So this variety is the one that I need to compactify to understand the sheaf cohomology of this variety with coefficients in a sheaf, which comes from this cover. So this is like an SN action. And then using that, I construct sheaves, but I need to compactify this one. And so the compactification is very simple. We embed it. We just embed into P1 to the n. And we take the closure. We take the closure in P1 to the n. So each alpha I, we extend that to a P1. And we take the closure there. And then the key theorem is that this closure is actually quite well behaved, and near a point in this closure, I have a local model for this variety, which gives it a very nice structure that I can use to do vanishing cycles calculations.
So this is where square root comes in.
Yeah. So exactly. So this, I mean, basically, when you have a congruence mod G for square free, you're looking at the values of this polynomial at m different points, and so that can be written as like xi minus alpha I product from I equals 1 to m is equal to c. The equations have this form, and that turns out to extend nicely to the compactification. If I had a non-square free, I would like take something on the derivative of this polynomial at a specific point, and then it would just be a lot worse. It turns out to have worse singularities at the boundary, at least as far as I can tell. And so for short intervals, I did something similar, except instead of taking P1 to the n, I just took Pn. So this is an affine space, I embed into Pn, and that one had nice singularities in that case. So probably there's something you can do. You can try different things to embed it in and see what works, but I didn't find anything.
Any more questions for Will?
Is it possible to ask from Zoom?
I think I just somebody said a question from Zoom. Let me.
Can you hear?
Yeah.
Like you said that the analogous assertion with polynomial values, like with Mobius functions and maybe things that you can derive from, but there is no obstruction that it will fail like for other f rows.
There's no function that could fail. What did you say?
Yeah, I mean that analogous version could potentially hold for all the f rows.
So okay, so I think what you were asking is like, so I said that I could prove a result in a restricted case only for Mobius, like about polynomial progressions for functions summed over polynomials of polynomials. I only proved the result for Mobius, or we proved that with Mark. And the question is, could it hold for other types of functions? Is there a reason it shouldn't hold? Like, I absolutely think it should hold for like the Velmango function, other types of functions. You sum it over polynomial progressions, there should be a nice asymptotic. Can you prove it? I have literally no idea what is in reach for proving, like over the function field model or not for these kinds of things. It might be there's just one really good idea that just solves the problem for an arbitrary factorization problem for polynomials. I don't know.
Thanks. So, thank you very much.
How many? Oh, I love it. Does anyone else have Zoom questions? Let's see who's there.
If there are no more Zoom questions either, then let's all thank Will again for a good